तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Good morning. Last time we derived a couple of expressions for the magnetic field in different geometries. Today what I am going to do is to connect up these calculations to a very important concept, namely inductance. We can't really formalize this concept of inductance till we reach Faraday's law, but I am going to introduce the definition and I will make it make sense once we have done stored magnetic energy. So, what have we done? We looked at an irregular solenoid and we concluded that the magnetic field is constant inside and 0 outside. We did that by proving that the magnetic field is in the z direction. And then if it is in the z direction, you can always draw Stokes loops, and since there is only magnetic field here and here, you have loop integral B dot dl is equal to B of R1 minus B of R2 times dl. But there is no current entering. It is supposed to be equal to surface integral J dot ds, which is 0. So, that must mean that the magnetic field is constant along this direction. Similarly, we worked out the case for an irregular torus and we proved that the magnetic field is equal to mu naught N I over 2 pi r inside and 0 outside. And the way we proved it was quite important. We proved it by talking about the vector potential A and showing that if the vector potential A has certain symmetries, in this case vector potential A is not a function of z, and because the currents are all in r theta, we said that A is equal to AR of r theta along the r direction plus A theta of r theta along the theta direction, where r and theta are, this is the r direction and this is the theta direction, polar coordinates. If you assume just this much, the rest follows. Similarly, here I had to work a little bit to show that the vector potential A was in the RZ plane. So, it was AR as a function of r and z along the r direction plus AZ a function of r and z in the z direction. Del del phi was equal to 0 and A phi was equal to 0. Using just that information, I was able to prove this. These kinds of proofs are quite important. I mean, after all, the solenoid and the toroidal solenoid are perhaps the most important magnetic structures we have in electrical engineering. So, if we can easily derive expressions for them, then there must be some use for this vector potential. Okay. So, now we have got some expressions. Let us look at what those expressions are saying. In the case of solenoid, and I am going to take a circular solenoid. There is no need now to go for irregular and other things. I have n turns per meter. I already know that B is along the z direction and is equal to mu naught n I, where the I is the current per turn, n is the number of turns per meter. So, Bz is in the z direction, and in fact Bz is constant within the solenoid. Now, this is true for an infinite solenoid. For a finite solenoid, there are always going to be end effects. So, if you had a solenoid that is only a length Lz, what will happen is, in the middle of the solenoid you will have uniform B, but it will start diverging as you reach the ends. So, what happens is, actually a little bit of flux leaks out through the side coils towards the end. So, it is not true that B is totally along Z, and it is not true that the amount of B that is enclosed is constant. So, it is an approximation for finite length solenoids, but it is exact for an infinite length solenoid. Now, I want to introduce a new concept, which is, I have this solenoid and the solenoid has a cross section, in this case a circular cross section. So, just as for displacement vector I defined the amount of flux leaving a surface, of course in that case I used closed surfaces, and I talked about this as the electric flux leaving a surface. Similarly, I can talk about a magnetic flux leaving this surface. So, I can talk about surface integral B dot ds. It turns out to be an extremely important concept, and it is called the magnetic flux, usually denoted like this. In fact, very often you will not even see the m below, it is just phi. So, this magnetic flux is the integral of B over a surface. Which surface? Well, it does not matter which surface, because supposing I have some loop and I connect it by a surface. I could also connect it by some other surface. So, one surface is along the plane, the other surface is pulled out. So, I would get different answers perhaps, but I will not, because if I call this top surface say 1 and I call the bottom surface 2, then I can do something. I can say the surface integral of 1 B dot ds minus the surface integral over surface 2 B dot ds. Now, what does minus surface integral mean? It really means plus minus B dot ds. I can always take the minus inside, which means here B is pointing upwards, there I am taking the opposite sign, I am asking B to point downwards. In that case, what does this mean? This is nothing but integral over the entire surface B normal dA, because on this surface I am doing B dot ds, on the bottom surface I am doing minus B dot ds. So, I am taking the total amount of B that is trying to leave this volume. So, that is surface integral over the closed surface B dA. But we know Gauss's law, the divergence theorem tells us this is nothing but volume integral over the enclosed volume some V divergence of B dV. This is just coming from the divergence theorem. Any vector field dot dA over a closed surface is equal to an integral over the enclosed volume divergence of the vector dV. But now I have a well known result. I know that divergence of B is equal to 0 everywhere. It is a fundamental statement, and it came out of the fact that B is an integral of j cross r over r cubed. So, divergence B is 0, which means this is 0. So, it says integral over surface 1 minus integral over surface 2 is 0 for any pair of surfaces 1 and 2. But what does that mean? It means integral over 1 B dot ds is equal to integral over 2 B dot ds for any surfaces 1 and 2 that connect to the same closed curve. That is the only condition, that 1 and 2 must somehow connect to the same curve. Now, note that this curve does not even have to be on a plane. I have drawn a curve that is like a cucumber, right. I can draw a surface that look like this, and I can draw another surface that looks like this, and the top surface and the bottom surface will both give me the same answer, which means what this means is that talking about magnetic flux is meaningful, and I think that is an important point. See, when we talked about electric field, we defined a quantity phi which was minus integral from infinity to r E dot dl, and we did not know whether this thing was meaningful or not. We could only say it was meaningful because it did not depend on how we got from infinity to r. Once we knew that, then we had a powerful new concept called the scalar potential or the electrostatic potential. Now, similarly here, B is some vector field, it is a complicated field, but you find that if you integrate B on any surface that connects to a closed curve, no matter what that surface is, you get the same answer, which means that this concept of phi magnetic is a good concept. It does not depend on how I drew my surface, any surface will do. So, it is very analogous to talking about electrostatic potential. So, you should see these two as analogues. Now, if you see these two as analogues, then you can ask potential is stored in capacitors, right. I mean, potential, you have a relation Q equals CV, and voltage is nothing but potential. So, there is a characteristic of potentials that is coming into circuit devices. Similarly, the moment you define something that does not depend on the detailed shape of electromagnetic objects, you can expect that it will enter a line diagram. See, it is quite important here, so pay attention. Supposing I draw a circuit and I wrote this, and I said there is a capacitance C. Now, if the behavior of this object, the relationship between current entering and the voltage was a very complex function of the shape of this object, if it depended on where the current entered, if it depended on which part of the capacitor was where, then you won't be able to write a simple relation like Q equals CV. It will become much more complicated. It would depend on the distribution of charge, it would depend on other things. Once it did that, it would no longer be useful in circuit theory. But we know ahead of time that capacitor is a very well defined object. It is defined by a scalar equation. So, all the vector details are hidden in C, and that comes out of the fact that actually you have certain linear relationships that define what is happening inside C, and you have a scalar quantity, the potential, that does not care about the path by which it is calculated. All these things go into making this possible. Similarly, now we have a new scalar quantity, it is called magnetic flux. Now, it is a scalar quantity that is a function of an entire loop, but it does not depend on the surface that connects the loop, and we can confidently expect that because there is such a simple idea here, that there is another circuit device that is connected up with this scalar quantity, and of course that is the inductance. Inductance is the connection between magnetic flux and the current through the coil. Just as in capacitors, capacitance is the connection between the potential and the charge that is stored. So, stored charge and the current that is flowing through the coils are the quantities that directly define the fields. The charge is what generates the field here, current is what generates the field here. Associated with the charge, there is a concept called electrostatic potential. Associated with the current, there is a quantity now which we have found, which is magnetic flux. So, there is a big symmetry here, and it is very important to appreciate it, because every time you see a symmetry between electrostatics and magnetostatics, you should use it to simplify magnetostatics. You should not get confused and frightened by the fact that magnetostatics seems to use much bigger formulae. It is almost for point to point the same as electrostatics. You just have to appreciate the fact that it is the same thing, and then things become much simpler. Okay, I am going to now introduce what is the definition of inductance, but as I said, this definition won't make sense till we get to Faraday's law. So, we assume that there are many coils, they are all connected up. So, you have a current I, this current is also flowing through the other coils. Since it is a very common arrangement, we always work with coils in electrical engineering. So, we have built the concept of inductance. In the concept of inductance, we have built into it the number of turns per meter. We could actually have defined inductance per turn and then generalized for an n turn system, but it is so common to have multi-turn coils that we just built the number of turns per meter into the definition of inductance. So, let us say we have n turns per meter. Now, each of these turns, there is a current, and that current is trying to create a magnetic field. So, if the current is going this way, the magnetic field is like this. Now, the next turn is trying to produce its magnetic field, third one is trying to produce its magnetic field, fourth one is trying to produce its magnetic field. And from this picture, you can easily see, if you added them all up vectorially, you are basically going to have a magnetic field that goes like this, which is what we derived last time. A uniform magnetic field inside the solenoid, diverging magnetic field on entry and on exit. It is converging on entry and diverging on exit. Now, what is worth knowing is that when we derived it, we found for a solenoid that the magnetic field in the interior of the solenoid Bz is equal to mu naught I times n. That is, the magnetic field is stronger if you have multiple turns. But it is not the total number of turns in the solenoid that matters, it is the number of turns per meter, per unit distance. So, if you tightly wind this solenoid, you get a strong magnetic field. A solenoid could have 400 turns and the B field is not 400 times, not if the 400 turns are stretched over 10 meters. Then it is only 40 turns per meter, so the magnetic field is only 40 times. So, this n is turns per meter and not total number of turns. Now, the definition of flux you would imagine would be phi is equal to surface integral Bz dA, which is nothing but mu naught Ni times area. Now, we define inductance as the relationship between phi and I, but not really between phi and I. We say that this magnetic flux is seen not just by one coil, but it is seen by n coils. So, we define inductance L as the flux that links n coils per unit current. As I said, this concept of putting in the number of turns is more for convenience. You could have defined flux per coil and inductance per turn, and then you would have worked out that there would be an n squared factor coming into the answer. But because it is so common to have coils, we have put the number of turns per meter into the definition of inductance itself. Now, if we put back the definition of phi into this, what do we get? It is equal to n over I times mu naught Ni times area. Since the flux is proportional to current, if you divide by current, the current has to go away. So, you are left with mu naught n squared times the area. The inductance is proportional to the square of the number of turns per unit length that you wind around your solenoid. This is generally true. You will always see an n squared. It is because the magnetic field you produce is higher because of the number of turns, and you are linking n coils with that same magnetic field, and therefore, you get n twice or n squared. You can work out the inductance due to many other geometries. For example, supposing we had our torus, then I am going to choose a square cross section. That simplifies the maths. So, my inner radius to the center of symmetry is a distance a, outer radius is a distance b, the height is Lz. We worked out that if you take this solenoid, that the magnetic field is purely in the phi direction. Therefore, you can apply Stokes theorem and say 2 pi r b phi equals mu naught I. But there are n turns, so I put an n, because when it goes round, it's all these currents are coming out. So, the number of turns is the total number mu naught capital N I. Let me show it from above. You have your inner wall, the outer wall of your solenoid. You are looking at magnetic field somewhere, some radius. So, you take a loop like this. This loop has a length 2 pi r times b phi. Coming out of this inner wall are all these coils. So, the total number of turns, not the turns per meter, but the total number of turns is what is getting linked by this loop. So, I have put a capital N, and this capital N is equal to mu naught times 2 pi a n I. 2 pi a is the circumferential length around the inner wall, and n is the number of turns at the inner wall per meter. Okay, so what do I get? I get b phi is equal to mu naught n I times a over r. The 2 pi will cancel out. If we kept it in terms of capital N, it would have been mu naught capital N I over 2 pi r. Both are okay. You have to decide which form of the definition you want. Now, this is the magnetic field. We need the magnetic flux. Now, it is important here to understand what surface we are talking about. The current is flowing like this, and then it is coming back to the next coil, and so on. So, the current is flowing in the RZ plane. The magnetic field is in the phi direction. So, the surface we are talking about is the surface that links this coil. So, phi magnetic is equal to surface integral of z going from say 0 to Lz, r going from a to b, dr dz of b phi, which is mu naught n I times a over r. The integrals are trivial. It gives you mu naught n I times a times the z integral. The integrand is not dependent on z, so I can just integrate it trivially Lz. The integral in r has a 1 over r in it. Integral of 1 over r is log. So, the answer becomes ln b over a. That is because integral a to b dr over r is equal to ln r between the limits a and b, which is ln b minus ln a, or ln of b over a. All right. So, I have got ln of b over a. So, this is the flux per turn. So, inductance is now going to be n of the times this phi divided by I, or it is equal to mu naught n squared times a Lz ln b over a. Now, it depends very much on how you define your n, because I have defined my n as number of turns per unit per meter on the inner wall. Since the dimensions of such a system is varying as you increase in r, I could have defined my n as number of turns per meter on the outer wall. Then I would have got a different expression. But whatever expression I use, I will always have n squared. Once again, inductance depends on the square of the turns per meter. Let us take a third example. coaxial cable. I have an inner radius of my wire is A, outer radius is B. So, the current goes, let us say, up I z in the inner wire and comes back down on the outer wire. Because of the symmetry, I can again calculate B. Stokes' theorem tells me 2 pi r B, since the current is in the z direction, B is in the phi direction, is equal to mu naught I. There is only one turn. This is not a case with n turns. This is a single turn, single wire that is going up and coming back, bringing current back. So, this is the total current, single coil. So, B phi is equal to mu naught I over 2 pi r. What is the flux? The flux therefore is the cross section. I have to take flux is what intersects this cross section, because it is a phi direction B phi. So, the cross section is in R and Z. So, phi magnetic is equal to integral, say, 0 to some Lz integral A to B mu naught I over 2 pi r dr dz. It is the same integration. So, we get mu naught I over 2 pi times Lz times ln B over A. So, this is the magnetic flux, it is proportional to current. So, I can define an inductance. Inductance I will define will be phi over A, phi over I, because there is no n is 1. So, I get mu naught over 2 pi Lz ln B over A. So, the inductance in this example is proportional to the length. That is not surprising, because the more length of wire I take, the greater amount of flux I am linking, and therefore, the more inductance, because inductance is nothing but flux per unit current. Okay, we will come back to the concept of inductance later on. There is no point going further till we define Faraday's law. I want to turn to another topic right away, which is the topic of matching conditions for magnetic field when you have a boundary. In electrostatics, we had developed matching conditions. What were the conditions we had? We had that normal component of D is continuous and tangential component of E is continuous. We proved this using Gauss's law and Stokes' law, Gauss's law and Stokes' theorem. Namely, we had some surface, there was, say, epsilon 1 on one side, there was epsilon 2 on the other side. I put an imaginary cylinder, a cylinder that was very, very thin. So, even this picture is not very correct. A better picture would be like this. It is a small cylinder, but its surface area at the top and bottom is much larger than its side area. Now, I try to do integral d dot ds. There is no free charge enclosed, so I got 0. and using that I came up with continuity of normal component of D. And for continuity of tangential component of E, I used Stokes theorem and I used curl of E is equal to 0. We have to do the same thing now. We have to use corresponding equations in magnetic field. Well, we do know that volume integral B dot ds is equal to 0 always. This is fundamental because divergence B is identically 0. Using this condition, which is the same as this, we were able to say normal component of D is continuous. So, apply surface integral B dot ds equals 0 to this cylinder. What will happen? Your magnetic field is doing something. The sideways fields will contribute to the sloping sides, but we are taking a cylinder that is so flat, the sloping sides have almost no area. So, all the contribution is coming from the top and the bottom. So, I get, if this side is 1 and this side is 2, I get surface integral, I am assuming the directions the way they have drawn. So, minus surface integral B dot ds along surface 1 plus B dot ds on surface 2 is equal to 0. Because in one case it is entering, the other case it is leaving. What does that mean? It means surface integral over surface 1 B dot ds equals surface integral on 2 B dot ds. But this can be written as integral over 1 B normal dA is equal to integral over 2 B normal dA. Areas are the same, and if it is a small enough cylinder, B is uniform over that surface. So, this finally gives me my result, which is that B normal 1 times the area is equal to B normal 2 times the area, or B normal is continuous. This exact same derivation as what we did for displacement vector. But you will see that in displacement vector we had to make an additional approximation or additional assumption, which was there is no free charge on the surface. Here this is absolutely true. It does not depend on whether there is current or charge on that surface. It is always true that divergence B is 0. So, it is always true that B normal is continuous at any surface. Okay. Now, what about the other condition? Well, we use curl of E is equal to 0 to prove that E is continuous. Let us use curl of H. Curl of H is equal to J, Ampere's law, which means that I can now look at this surface and assume that there is no free charge, a free current. This is the equivalent of what I did for D. Supposing the surface is only a surface between dielectrics, so there is no free current there, it is equal to 0. If curl of H is 0, then I can use the same argument I used for proving E is continuous. So, I take a long loop so that the vertical sides are negligible in length. Again I have my field, this is H, and the field does something in the other side. So, I call this side 1, I call that side 2, and I go round this loop in some direction. Then I have this statement is equivalent to saying loop integral h dot dl is equal to 0, that is integral on side 1 h dot dl plus integral on side 2 h dot dl is equal to 0. But if I do integral on side 1 h dot dl, that is h1 tangential times dl. On side 2 it is minus h2 tangential same dl is equal to 0. The minus sign came because I am integrating in the reverse direction. What does this mean? It means that h1 tangential is equal to h2 tangential, or tangential component of h is continuous if no free current is present. Now, why did I use h here? Why couldn't I have used b? Let us try to use b and let us see what goes wrong. Okay. So, I am going to follow the same steps and see what goes wrong when I use b. I will use curl of b is equal to mu j. Now, when I do this, there is a problem. Let me show you what the problem is. I do a loop integral. So, I say loop integral b dot dl is equal to surface integral mu j dot ds. Now, j free may be 0, but anytime I have two magnetically sensitive materials with different permeabilities mu 1 and mu 2, what is going to happen is at the surface boundary between these two there is going to be a surface current. This surface current represents the fact that the amount of induced spinning in this material and the induced spinning on that material are different. So, on this surface alone there will be a large surface current, which means that mu j cannot be set to 0, or if you like, I should not call it mu j, I should call it mu naught j total. So, then it will be mu naught j total, which can then be written as surface integral mu naught j bound. So, it is this term j bound which is not 0. I do not have any free current on this surface, it is a non-conductor, but I do have induced current on this surface, and this induced current is going to cause a contribution, and because it is going to give a contribution, it is not true that tangential component of B is continuous. In fact, if tangential component of H is continuous, what does it imply? It implies that tangential component of B is not continuous, because H1 tangential is equal to H2 tangential, but H is nothing but B over mu. So, B1 tangential over mu 1 is equal to B2 tangential over mu 2, or B1 tangential is equal to mu 1 over mu 2 B2 tangential. So, there is a jump in B tangential. B normal is continuous, B tangential is not continuous, but H tangential is continuous. We will use all these matching conditions little later when we come to dealing with magnetic circuits, talking about what happens when you enter a magnetic material and when you leave it. Now, I want to just touch upon one important topic in the rest of this lecture, and that is the topic of what happens to free charges when they are in the presence of electric and magnetic fields. Up to now, what have we done? We have talked about charges in the presence of electric fields and currents in the presence of magnetic fields. But what happens if I put a free charge and apply electric and magnetic fields? I know that my force equation according to Newton is m dv dt, rate of change of momentum, is the applied force. Now, what is this applied force? It is the electric force QE plus the magnetic force, which is Q V cross B. QV is like J, so this is nothing but J cross B. And this, if it is an electron or a piece of the fluid, also suffers from viscous forces. So, you can put a drag minus m nu v. I am talking about a particle. So, this particle, let us say it is a, you can be doing the Millikan oil drop experiment, or you can be talking about the Hall effect. Any of these will satisfy an equation similar to this. The rate of change of momentum is equal to the applied electric force plus the applied magnetic force minus the drag on the particle. The drag here is modeled as a nice simple model where I am assuming the frictional coefficient of friction is a constant. Now, I am looking only for steady state problems. I do not want to look for time dependent solutions, because that is a more complicated situation. So, I am going to say steady state, the left hand side is 0. So, I am looking for constant velocity solutions. Let us look at some simple solutions then. Supposing I say B is 0. We have already done this problem. What does it give us? It gives us QE minus m nu v is equal to 0, or taking m nu v to the other side, I can solve for v. V is equal to q over m e divided by the coefficient of friction. So, q over m e is the acceleration, and the acceleration is balanced by a slowing down friction, and when these two forces, or when these two accelerations balance, that gives us the steady velocity. This is nothing but Ohm's law, because inside a material what is happening is you have a steady electric field and you have a steady frictional force. Of course, you have, there is also a statistical component to it, because each electron that is moving with a different velocity, and it is only on average that this equation is satisfied. But if you asked what is that average velocity that the electron has, it is given by the balance between acceleration due to electric field and drag due to collisions. So, this is our Ohm's law, which we are very familiar with. Now, what happens if I have a magnetic field present as well? Well, my equation becomes QE plus QV cross B minus m nu v is equal to 0. Now, I am going to simplify this problem by assuming certain directions. This is the x, y, z direction. I will assume the magnetic field is along z. I will assume the electric field is along x, and I want to solve for the velocity. So, the stationary electron or stationary particle feels only the electric field, but as it starts moving, it feels the magnetic field through the V cross B force. So, let us try and imagine what will happen if I start with a particle at rest, let us say there. The first thing it will do, it will start falling in the x direction, because there is an electric field present. It needs to catch up till its steady state velocity is reached. But even as it starts moving, there is now a V cross B force, and the V cross B force is in this direction. Because of the V cross B force, now the particle starts moving in the minus y direction as well. So, it starts bending over. But when it starts moving in the y direction, once it has a Vy, then it has a minus force in the x direction as well, because Vy cross Bz is in the x direction. So, there is a force in the x as well as a force in the y, and these two forces together, when they are both present, is what will give us a final balance of forces in this equation. So, velocity is equal to Vx x plus Vy y. The electric field is only in the x direction, the magnetic field is only in the z direction. Let us see where it gets us. So, I have Qex along x plus Q Vx Bz, x cross z is minus y, plus Q Vy Bz, y cross z is plus x. So, the V cross B term gives me two terms. The Vx cross B gives me a minus y direction force, the Vy cross B gives me a plus x direction force. Then minus m nu Vx along x minus m nu Vy along y. The whole thing is equal to 0. So, these are two equations, because there is an equation connecting all the components along x and an equation connecting all the components along y. Let me write them down. Qex plus Qvy Bz minus m nu Vx is equal to 0, and minus Q Vx Bz minus m nu Vy is also equal to 0. So, this is the x direction force balance, this is the y direction force balance. Both of them must hold, and I have two unknowns. I do not know Vx, I do not know Vy. Two equations, two unknowns. Let us solve this equation first. It allows me to solve for Vy in terms of Vx, or the other way around. Vy is equal to minus Qbz over m nu Vx. I just take the m nu to the denominator. Now, I have a very important quantity called the gyro frequency. This gyro frequency is the speed at which particles go round and round the magnetic field. We will come back to this later. Right now, just note that this is a well known frequency. So, I can write this as minus gyro frequency omega over nu Vx. Similarly, I can take this equation, and what do I get? I get that I will divide through by m nu Qex over m divided by nu plus Qb over m, so omega over nu Vy minus Vx is equal to 0. But I already know Vy in terms of Vx, so I can substitute here. So, I get Qex over m divided by nu minus omega squared over nu squared Vx minus Vx is equal to 0. Or if I solve, I get the answer Vx is equal to Qex over m divided by nu. This is the force, balance of forces that in the absence of magnetic field would give me a stationary velocity, but it's multiplied by 1 over 1 plus omega squared over nu squared. So, if the magnetic field is 0, this is the drift terminal velocity. If the magnetic field is very strong, then what happens is it is the magnetic field that acts as a friction. It is not the collisions that act as a friction, and the x velocity basically becomes 0. What does Vy look like? We know that Vy is minus capital omega over nu Vx. So, it becomes Qex over m over nu omega over nu, the minus sign, divided by 1 plus omega squared over nu squared. So, Vy is much larger than Vx when magnetic field is strong. So, it's in a case of strong magnetic field, what happens is there is nu squared that cancels out, and it's only magnetic field that gives me drift. Let me work out that case. Vy is equal to Qe over m times the nu squared has cancelled out, omega over omega squared plus nu squared. This is called the E cross B drift. This E cross B drift is present in any magnetic field with or without friction. This drift is really a modified Ohm's law. It is an Ohm's law in the presence of magnetic field, and it is from an effect like this that you get things like Hall effect and MHD power generation and other effects like that are quite interesting to electrical engineers.